Okay, calculus, math 175. This is lesson 17 on the syllabus, which has to do with extrema on an interval. So why people like to use this old Latin word extrema is, I don't know, but the idea is very simple. You could have a graph of a function that looks like this. And at this point, the function, it's not the biggest it is anywhere because it's bigger over here, but in some little interval around this point. In this interval, the function is bigger here than it is anywhere else. So this is what is called a relative, or sometimes called a local maximal. It means that in this, around this point, the function is as large there as it's ever going to get. And similarly, if you look at this point, it's not the smallest value, it's not the lowest point on the graph, its graph is lower over there, but at least in some interval around this point, the function value is less here than it is anywhere nearby. And such a point is called a relative or a local minimum. And when we're trying to understand the function, one of the first things we look for is where it has a relative maximum or where it has a relative minimum. And it can have many. I mean, you can have a function that looks like this. This again, right here, is another relative max. This is another relative min. This is another, relative max. This is another relative max. This is a relative minimum. This is a relative minimum, and so forth. So a function can have many relative maxima and many relative minima, either on the whole line or even if it's only defined in an interval. But they do describe, they do give us very basic information about what the graph looks like. So for example, if you had a cubic curve, I don't know, I'll make up some numbers. It turns out this function has one minimum and one maximum. And it goes to infinity as x gets bigger and bigger, and it goes to minus infinity as x gets smaller and smaller. So you would think it's like going to negative infinity in this direction, then it hits a maximum, then it has a minimum, and then it goes up. So just knowing that a cubic curve usually has exactly one relative maximum and one relative minimum automatically gives the shape of the curve. Now we have to find out where these points are, but we know it's going to go up, turn around, come down, turn around again, and go up forever. So having some idea of these relative maxima and minima is really important. Okay. Now, you could have a function, suppose you have f of x defined maybe just on a closed interval, say x between a and b. So let's say this is 0, A, and B. And the graph of the function looks like that. So if you look at this, in this interval, here we have a relative max. Here we have another relative max. Here we have a relative min.
Professor, can you move the paper? Thank you.
Right? So this function is just defined on some interval. In this case, it's a closed interval. And the graph looks like that. So we have, in this instance, 2 relative maxima and 1 relative minimum. But we can also ask for the absolute maximum and the absolute minimum. So this means on this interval, the absolute maximum is the point where the function is bigger than it is anywhere else. And in this graph, for example, this point right there, that's the absolute maximum. It happens to be a relative maximum, but there's another relative maximum. This one's the absolute maximum. And what is the smallest the function ever gets on this interval? Well, right down here. This point is the absolute minimum. Because at this point, it's smaller, it has the smallest value of any point in the interval. Okay. So we have 2 different notions. We have the relative maximum and minimum. This is a relative maximum and this is a relative minimum. And we have the absolute maximum and the absolute minimum. This is the absolute max. This is the absolute min. Sometimes people don't use the word absolute. Sometimes they might use the word global. So this might be called the global maximum. And this might be called the global minimum. And sometimes people don't use either of those words. They just say the maximum or the minimum of the function f on an interval. But it always means the biggest value the function takes on, or the smallest value the function takes on anywhere in the interval. Okay. So this is a very important geometrical notion in calculus. Relative minimum, relative maximum, absolute minimum, absolute maximum. Now, there's a connection between the derivative of the function and where it has its relative maxima and minima. And let's see. So there are 2 theorems about this. Yeah, okay. So the first theorem says the following. On a closed interval means an interval that contains the endpoints. We usually write a closed interval from A to B as square brackets around the A and B. So this means all x which are greater than or equal to A and less than or equal to B, every continuous function has an absolute maximum and an absolute minimum. So if the function is continuous, there always is at least one absolute max and absolute min. There can be more than one. So for example, suppose we consider just the simple function f of x equal to the sine of x for x between 0 and 6 pi. What does the graph of the sine look like? Well, the sine goes from, as you go from 0 to 2 pi, sine oscillates like that. From 2 pi to 4 pi, it oscillates again. From 4 pi to 6 pi, it oscillates again. It oscillates again. That's the graph of the function. For sine of x, the absolute maximum is 1, right? 1 is the biggest this function ever becomes. And this occurs, actually, it occurs 3 different times in this interval. At x equal pi over 2, 2 pi plus pi over 2, which is 5 pi over 2, and 4 pi plus pi over 2, which is 9 pi over 2. So this maximum, the absolute maximum, is 1, and it actually happens to occur 3 times. Similarly, if you look at this graph, the absolute minimum is -1. So it's -1. And when does it occur? Well, it occurs here, x equal to 3 pi over 2. It occurs here. This is 7 pi over 2. And it occurs here, which is 9 pi over 2. So the theorem says that a continuous function, and the sine of x certainly is continuous, continuous function always has an absolute maximum and an absolute minimum on a closed interval, but that absolute maximum and absolute minimum can occur more than once, right? So in this instance, if we take the interval to be from 0 to 6 pi, the absolute maximum occurs 3 times, the absolute minimum occurs also 3 times. Okay. Any questions about this? Now, what can we say about the relative
Professor, I have a
maximum?
question.
Yeah, go ahead.
So the absolute maximum and minimum can be more than one. So like in sine and cosine, the absolutes are more than one.
Well, right, it's exactly what you see here.
So all of those values would be the absolute.
Well, there's one absolute maximum. The absolute maximum value is 1. But that happens in this interval, the function is equal to 1 3 different times.
Oh, okay.
So there's only one absolute maximum of the function, but the function can hit that maximum more than one time. Okay?
All right, thank you.
All right. Now, In order to understand relative maxima and minima, we need the definition of what's called a critical number of a function. F of x. A critical number is just a point where the derivative is zero, almost. So let f, the function f, be defined at x equals c. The number c is a critical number of f if either the derivative of the function at c is zero, or there's no derivative. The derivative of f does not exist at the point x equals c. So for example, if f of x is equal to x squared, f prime of x equals 0, f prime of x is 2x, and that's equal to 0 when x is equal to 0. So x equals 0 is a critical number of this function. At the point x equals 0, the derivative is 0. If you have the function f of x equals the square root of x, what does the graph of that look like? Sorry, not absolute value of x. It's just this function. So we know that f prime of x is 1 if x is bigger than 0. F prime of x is minus 1 if x is less than 0. And there is no derivative at x equals 0. At x equals 0, the derivative isn't defined. So x equals 0 is a critical number for the absolute value function. So a critical number is a number where the function is defined and either the derivative is 0 or there just is no derivative. The derivative doesn't exist. And the really important theorem in this part of calculus says the following. If the function f of x has a relative maximum or a relative minimum at x equals c, then c is a critical number of the function. So if you're going to have a relative minimum or a relative maximum, or if you have a relative minimum or a relative maximum at a number c, that c is a critical number of the function. So the derivative is 0 at c, or the derivative doesn't exist at c. And we can observe that in the two examples we saw a moment ago. Suppose we have the function y equals x squared. That's the graph of the function. The point c equals 0 is a relative minimum. What is the derivative of this function? dy dx, or f prime of x, whatever notation you prefer to use, is 2x, and f prime of c, that's f prime of 0, is 2 times 0 is 0. So c is a relative minimum, and the derivative is 0 at this point. So c is a critical number. So 0 is a critical number. What was the other example we looked at? Y equals the absolute value of x. The graph looks like that. For this function also, c equals 0 is a relative minimum. The derivative of f of x equals the absolute value of x. There is no derivative at 0. It does not exist at x equals 0. So therefore, 0 is a critical number of f of x. So here we have two examples of functions with relative minima. And in both cases, at that point where the relative minimum occurs, you have a critical number. In the first case, because the derivative exists and equals 0. In the second case, because the derivative doesn't exist. Okay. So this is very important to understand, and I'm going to sketch a proof of the theorem. So let C be a relative max or min of the function y equals f of x. So if the derivative does not exist at C, then we're done. If the derivative doesn't exist, C is a critical number. Suppose f prime of x does exist at C. So that means if you take the limit as x approaches C of f of x minus f of c over x minus c, that limit exists and it's equal to the derivative, right? This is the definition of the derivative of the function at C. So let's suppose x equals c is a relative minimum. So what does our function look like? Roughly speaking, here's the graph of y equals f of x, and f of c is a relative minimum. So what does this mean? It means that if x is bigger than c and close to c, then f of x is greater than or equal to f of c, because the function is smaller here, or no bigger than it is anywhere around it. So if you take a point x bigger than c, f of x is greater than or equal to f of c, which means what? It means that f of x minus f of c is greater than or equal to 0. If x is bigger than c, x minus c is positive, you can divide by it. So if x is bigger than c, then f of x minus f of c over x minus c is greater than or equal to 0, which means the limit of f of x minus f of c over x minus c, as x approaches c from the positive side, this limit is going to be greater than or equal to 0. And this limit is the derivative. This means the derivative is greater than or equal to 0. So this is really a very important mathematical reasoning. Here you have a function with a relative minimum at c. So if you take x to the right of c, x bigger than c and close to c, f of x is greater than or equal to f of c. So this difference quotient, f of x minus f of c over x minus c, is non-negative. And so if you take the limit as x approaches c from the right, this limit, which is the derivative, is non-negative. So f prime of c is greater than or equal to 0. Right? That's the first case. The second case is, well, maybe you take an x which is less than c. So if x is less than c, again, since this is a minimum, f of x is going to be greater than or equal to f of c, which means f of x minus f of c is greater than or equal to 0. Now, x less than c means x minus c is negative. What happens to an inequality if you divide by a negative number? It reverses the sign. So f of x minus f of c over x minus c is going to be less than or equal to 0 whenever x is smaller than c, which means if we take the limit as x approaches c from the negative side, the limit's going to be less than or equal to 0, which means, but the limit is the derivative. The derivative is less than or equal to 0. So what do we have? We have that the derivative has to be greater than or equal to 0, and it has to be less than or equal to 0. And the only way that can happen is if the derivative is in fact equal to 0. So that proves if you have a function with a local minimum at c, and if the derivative at c exists, then the derivative at c must be equal to 0. So c is a critical number. And the proof of the theorem in the case of a relative maximum is essentially the same thing. So wherever you have a relative minimum or a relative maximum, you have a critical number, which means either the derivative is 0 or it doesn't exist. Now, okay. Any questions about that? This is really one of the most important theorems in calculus. So how do you find a relative minimum or a relative maximum? Well, find the critical numbers and, well, let's say, look at the graph of y equal f of x at the critical numbers. Those are the only places where you can have a relative minimum or relative max. How do you find the absolute minimum or maximum let's say on a closed interval. So we have the integral from a to b, and we have our function, and we want to find the absolute max and the absolute min. So step one, find the critical numbers. Step two, evaluate. As you can find the critical numbers, and it's enough to look at just the open interval, because we're automatically going to look at the endpoints. Evaluate f of x at the critical numbers. Also, evaluate f of x at the endpoints of the interval from a to b. That is, calculate the value of the function at a and the value of the function of b. And then we're done. The smallest number you get by evaluating f at the critical numbers and the endpoints, the smallest is the absolute minimum. The largest is the absolute maximum. Okay. So that is the algorithm or the recipe, if you like.
Wait, Professor, can you go back to that page?
Sure.
Thank you. Okay, thank you.
Mm-hmm. Okay, so let's look at examples. So in the text, this is example 2. Find the absolute extrema. The book just says extrema, but when it doesn't say relative extrema, it means absolute extrema of the function f of x equals 3x to the fourth minus 4x cubed on the interval from -1 to 2. So what are the critical numbers? We have to find the points where the derivative is 0. What is the derivative? Well, f prime of x is 12x cubed minus 12x squared. That's 12x squared times x minus 1, if you factor it. And when is this a 0? This equals 0 when x is 0 or 1. So these are the two critical numbers. What is f? Let's make a little table. I'll put in different values of x and I'll compute f of x. So we need f of x at the critical numbers 0 and 1, and also at the endpoints of the interval, -1 and 2. So f of 0 is 0. F of 1 is -1. F of -1 is 3 plus 4 is 7. And f of 2, 2 to the fourth is 16, times 3 is 48. X cubed, 2 cubed is 8, times 4 is 32. So 48 minus 32 is 16. So you look at these numbers. This is the maximum, the absolute maximum. This, because that's the biggest of the four numbers, and this is the smallest. So that is the minimum. And if you were to graph this, either by looking at the book or even better, using Maple, from -1 to 2, it's 0 at 0, it's -1 at 1, it's 7 at -1, it's 16 at 2, and the graph of this function actually looks something like that. And that is the absolute maximum, and that is the absolute minimum. So that's how we solve the problem. Let's look at another example. In the text, this is example 3. We have the function f of x equals 2x minus 3x to the 2/3. And we want to look at this function on the closed interval from -1 to 3. So if this is the function, what is the derivative? F prime of x is 2 minus 3. The derivative of x to the 2/3 is 2/3 x to the 2/3 minus 1 is minus 1/3. So this is 2, the 3's cancel, 2 over cube root of x. Of course, this is only defined, it's defined for all x except 0. So what are the critical numbers? X equals 0 is a critical number because the derivative is not defined there. Where the derivative is defined, f prime of x, which is 2 minus 2 over the cube root of x, when does that equal 0? It equals 0 if 2 equals 2 over the cube root of x, multiplied by cube root of x. 2 times the cube root of x equals 2. Cancel the 2's. Cube root of x equals 1. X equals 1. So x equal 1 is a critical number. So this function has two critical numbers, 0 and 1. So in order to find the absolute maximum and minimum, we have to evaluate the function at the critical numbers 0 and 1, and at the endpoints of the interval, -1 and 3. So when x is 0, we get 0. When x is 1, we get 2 minus 3 is -1. When x is equal to -1, what is -1 to the 2/3? Well, it's like taking the cube root of x squared. You square -1, you get +1. The cube root of that is 1. So we get 2 times -1, which is -2 minus 3, is -5. And when x is equal to 3, we get 2 times 3, which is 6, minus 3 times the q times the 2/3 root of 3. Which, if you use your calculator or look at the book, is approximately minus 0.24. So you look at these four numbers, which is the smallest? This one. So this is the absolute minimum. Which is the largest? 0. That's the absolute maximum. That's the story. It turns out if you graph this function, let's see, it's 0 at 0. It's minus 1 at 1. It's minus 5 at minus 1. And it's minus about a quarter at 3. And the graph of this function looks sort of like, comes up, has a sharp corner, there's no derivative there. Looks like that. And that's the minimum, and that's the maximum. All right. Any questions about this? These are really very important problems in calculus.
I just wanna be like I just wanna know if I have the right idea. So when we plot, we're basically plotting the critical numbers and the intervals, right?
So if you're trying to find the absolute maximum or minimum or both, you compute the value of the function at the critical numbers, and you look for and the boundary points, and you look for the largest and the smallest values. If you had to graph the function just from that data, you would do what I did. You plug in the values at those points, and then you try and figure out, using whatever tools you have in calculus or algebra, what the graph looks like. But normally you're not going, well, yeah, that's right. But to find the maximum and minimum, you don't need to look at the graph. You just have to compute this table. This table by itself gives you the answer.
Yeah, so the table, we basically compute the intervals which were at -1 and 3.
Yes.
And the critical numbers, right?
Right. It's the endpoints of the interval and the critical numbers.
Okay, thank you.
This is page 9. Okay. One more example. Again, in the text, this is example 4. We have the function f of x equals 2 sine x minus cosine 2x. And I want to look at this on the interval from 0 to 2 pi. So 0 and 2 pi are the endpoints of the interval. We need to find the critical numbers. Well, the derivative is The derivative of the sine is the cosine. The derivative of the cosine of 2x by the chain rule is plus the sine of 2x times the derivative of 2x, which is 2. And we want to find when is this derivative equals 0. See, this is the same as if I divide by 2, cosine x plus sine 2x equals 0. But you remember sine 2x is 2 sine x cosine x. So this is the same as cosine x plus 2 sine x times cosine x equals 0. And I can factor a cosine x out of this. I get cosine x times 1 plus 2 sine x equals 0. So I have to do this little bit of trig and algebra. And when is this equal 0? This equals 0 if and only if one or the other of these factors equals 0. Cosine x equals 0, or 1 plus 2 sine x equals 0. So we have to solve these two equations separately. Cosine x equals 0 when? Whenever x is pi over 2 plus any multiple of pi. So in the interval from 0 to 2 pi, pi over 2 or 3 pi over 2. Right? Remember the graph of the cosine from 0 to 2 pi looks like this. That's what the cosine looks like. And it's 0 at pi over 2 and 3 at pi over 2. So that's this first equation. The second equation, 1 plus 2 sine x equals 0. That's the same as 2 sine x equals 1, or sine of x equal to 1/2. So this is the graph of y equals cosine x. This is y equals sine x. For what values is the function equal to 1/2? Well, sine of x equals 1/2.
Professor, I have a question. Shouldn't it be -1 since we're moving the 1 to the other side?
Oh, thank you. Yes, negative 1/2. Excellent. So that's a good picture, but I want to find out when it's minus 1/2. So between 0 and 2 pi, when is the sine equal to minus 1/2? That happens when x is equal to, so it's going to have to be in the third and the fourth quadrants. X equals either 7 pi over 6 or 11 pi over 6. For example, if you have this angle, which is minus pi over 6 or plus 11 pi over 6, this is 1/2 root 3 over 2. The sine is negative 1/2. So we have 4 critical numbers and 2 endpoints. So we have to compute the value of f of x at the critical numbers. What are the critical numbers? For the cosine, pi over 2 and 3 pi over 2. For sine x equal minus 1/2, 7 pi over 6, 11 pi over 6, and at the endpoints of the interval, which are 0 and 2 pi. So I need to compute 6 values. Let's see. When x is 0, it's easy. You get 0 minus 1. When x is 2 pi, you get 0 and minus 1. What about when x is pi over 2? When x is pi over 2, let's see, let me just do the calculation. F of pi over 2 is 2 times the sine of pi over 2 minus the cosine of 2 times pi over 2, which is pi. Sine of pi over 2 is 1. Cosine pi is minus 1. So I get 2 minus minus 1 is 3. What about 3 pi over 2? F of 3 pi over 2 is 2 times the sine of 3 pi over 2 minus the cosine of 2 times 3 pi over 2 is 3 pi. What is the sine of 3 pi over 2? It's minus 1. And the cosine of 3 pi is minus 1. So I get minus 2 plus 1 is minus 1. I have to calculate 7 pi over 6 and 11 pi over 6. So f of 7 pi over 6 is 2 times the sine of 7 pi over 6 minus the cosine of 2 times 7 pi over 6, which is 7 pi over 3. The sine of 7 pi over 6 is minus a half. So this is 2 times minus a half minus the cosine of pi over 3, which is a half. So I have minus 1 minus a half. I have minus 3 halves. I'm just trying to squeeze this all in. And the last value is f of 11 pi over 6. That's 2 times the sine of 11 pi over 6 minus the cosine of 2 times this, which is 11 pi over 3. For 11 pi over 6, we saw we have minus a half. So this is minus 1. Cosine of 11 pi over 3, it's like minus pi over 3. That's plus a half. So minus another a half is minus 3 halves. So what are the values we get here? 5 are negative, 1 is positive, so this has to be the max. These two are the two smallest, so these are the absolute minimum that occurs at 2 places. And that's the story. Okay. Any questions about that? Let me do one more that I'll take from the homework. Ooh, up to page 10 already. So this looks like an interesting problem. Find the absolute extrema of the function g of t equals t squared over t squared plus 3 on the interval from -1 to 1. So g of t is t squared over t squared plus 3. To find the critical numbers, we have to see where the derivative equals 0. What is the derivative? By the quotient rule, square the denominator is the new denominator. The derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. So we get 2t cubed plus 3t minus 2t cubed over t squared plus 3 squared. These cancel. So we get 3t over t squared plus 3 cubed. The denominator is always positive. So the only time this is 0, it's 0 if and only if t equals 0. So there's one critical number. So we have to compute the value of the function at the critical number, which is 0, and at the endpoints of the interval, -1 and +1. When t is 0, we get 0 over 3. When t is -1, we get 1/4. When t is 1, we get 1/4. So this is the absolute max, and this is the absolute min. And in fact, if we were to graph this function,
Professor, I have a question.
yeah.
In the beginning where we were finding the derivative, it says 2t to the third plus 3t. Wouldn't it be plus 6t because 2t times 3
Oh,
is...
sorry. Right, 2t cubed.
Yeah.
Oh, plus 6t, correct.
Uh-huh.
Right, but we still get, this is 0 just when t is 0. Thank you.
You're welcome.
So the graph looks like this. We have a minimum, an absolute minimum at 0, and two absolute maxima, 1 at 1 and 1 at 4. So roughly speaking, that's what the graph looks like. Okay. So there are two topics for today and next Monday, two sections. The section on absolute, on extrema, and a section on Rolle's theorem and what is called the mean value theorem. What Rolle's theorem says is very simple. So that f of x be a nice, smooth, continuous function on the closed interval from A to B. And let f of x be differentiable. That means it has a derivative. On the open interval from A to B. I don't care for this purpose whether f actually has a derivative at the endpoints, if f of A equals f of B. Right. So we have this interval from A to B, and the graph of the function, whatever it looks like, it has the same values at the endpoints. So if f of A equals f of B, then there is at least one number C between A and B such that the derivative at C is 0. In other words, if you're going from here to here, you're going to have to, like, let's say you start going up, at some point you're going to have to come down, which means you have a relative maximum and the derivative is 0. Or if it turned out that from the point A you started to go down, you have to end up back up at the same height. So at some point you have to turn around and you have a relative minimum, and where you have a relative minimum, also the derivative is 0. Of course, relative maxima and relative minima occur at critical numbers. Okay. So let me just sketch a proof to motivate your understanding of why a theorem like this is true. So there are two cases, and the first case is trivial. Suppose f of x is constant. So f of x is equal to d for all x between a and b. And that's f of a and f of b, because function is constant. If the function is constant, then the derivative of x is equal to 0 for all numbers between a and b, because the graph is just a horizontal line. So if the function is constant, then it's kind of trivial. In case 2, f of x is not constant. So suppose we let d be this number, the value of the function at the endpoints, which is equal. Let's just call it d. So if the function is not constant, then for some number c, so there exists a c with f of c not equal to d. If it's not equal to d, it's either bigger or smaller. So suppose f of c is bigger than d. We know that the function has an absolute maximum. Right? So I'll just call this C1 just There's some point which is there where it's different from z. Suppose it's bigger. So let f of x have a maximum at the point C. So what we know about our function is it's equal to this number d at A and at B, and at some point it's bigger than d, which means the absolute maximum is bigger than d. And let's say the absolute maximum occurs at C. Well, C is not an endpoint, so it has to be a critical number. So f prime of C is 0. And we have a similar argument if at some point there's some number C where f of C is less than d. But the theorem itself, the geometrical meaning should be pretty clear. All it's saying is, here's y equals 0. Here's some height d. This is A and this is B. We have a function which has this value d at A and B. And so the graph has to go from here to here. If it's going up, if it's up somewhere, then it has to come down. If it's down somewhere, then it has to come up. And in both cases, you have a maximum or a minimum different from d. So the absolute max and minimum occurs inside the interval, and the derivative there is 0. Right? In other words, what goes up must come down. Right? What goes down must also come up. That's Rolle's theorem. Let me just show 2 examples of this, and then we'll be done. So suppose we have the function f of x equals x squared minus 3x plus 2. This is a parabola. What does the graph look like? Well, we know it's easy to find where it crosses the x-axis, at 1 and at 2. Right? So on the interval from 1 to 2, we have the x-intercepts, f of 1 equals f of 2 equals 0. What's the derivative of this function? F prime of x is 2x minus 3. That equals 0 when x equals 3/2. So there's this point 3/2, which is between the endpoints of the interval, where the derivative is 0. That's what Rolle's theorem says. Let's look at one other example. Suppose we consider the function f of x equal to x to the 4th minus 2x squared on the interval from minus 2 to 2. So if you do the calculation, f of 2 is 16 minus 8. So is f of minus 2. 16 minus 8 is 8. So f of 2 equals f of minus 2. So therefore, there exists at least one number c between minus 2 and 2 with f prime of c equals 0. Let's check. This is my function f of x. f prime of x is 4x cubed minus 4x. That's 4x times x squared minus 1. That's 4x times x minus 1 times x plus 1. And this equals 0 for x equal to 0, 1, and minus 1. So we in fact have 3 different numbers in the interval where the derivative is 0. Rolle's theorem tells us there's at least 1, but this tells us that they're in fact exactly 3. Any questions about this? Let's see, if you're keeping track, next Monday, we continue talking about Rolle's theorem and the mean value theorem. Wednesday, we talk about concavity. Then we have 2 other sections, one on limits and infinity and optimization. Then there's a review. And on November 18th, we have the second exam, after which we start to do integration. That's the schedule. Okay. Any questions about this? If not, then we are done for the morning. Be back next Monday. All right. Bye, everybody.